Now we would see the design of a progressive grading. In order to form a grading, the switches having access to the outgoing route are multiplied into a number of separate groups known as graded groups. In early choices, each group has access to individual trunks, and on the later choices, trunks are common. For example, in this figure 5.4, we can see that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. These are separate. These are individual trunks that go outwards, while 13th, 14th, 15th, and 16th are common for both the groups. This concept can be extended further, and what we can do is that we can have, instead of 2 groups, we can have 4 groups or even more groups. So if we want to find out the number of the availability of switching network, as you know that the availability is given by the term K, we can have n is equal to g into k, or k is equal to n divided by g, where n is the total number of outgoing trunks divided by g, which is the total number of groups. This is the same thing that we found out here. We have got 20 outgoing trunks and 2 groups. So the availability is 20 divided by 2, which is 10. So k is 10 over here. So the same formula is used here also. If so, the same formula, n is equal to k is equal to n over g, or n is equal to g into k, where g is the number of groups, k is the availability. If all the choices were full commons, which means that all are made common, or n is equal to k. Since the grading contains a mixture of individuals, partial commons and full commons, then k is then n is in between the value k and g into k, where g is the number of groups multiplied with the availability, and k is the availability. So n would come in between these two values, and the reasonable choice would be the value just in between these two. So we can say n is equal to 1 over 2 gk. The traffic simulations have shown that the efficiency of such a grading is near the optimum. So that is an optimal value. So the number of groups is thus chosen to be g is equal to 2n over k. Since the grading should be symmetrical, g must have an even number so that we can divide it equally. Otherwise, one trunk would be remaining if it is not even. So the value of g given by equation 5.3 is rounded up to the next even integer. So g here is, from this equation, g would be equal to 2n over k. It is now necessary to decide how gk trunks entering the grading are to be interconnected to n outgoing trunks. For 2-group grading, there is only one solution. If the number of columns of singles is S and the number of commons is C, then availability K is equal to S plus C, which is obvious. S is the singles and C is for the commons. So the number of trunks would be N, and the number of trunks would be N, which would be equal to 2 times 2S 2 times the singles plus C. So from these two equations we can have S is equal to n minus k and C is equal to 2k minus n.